All right. All right, here we go. Welcome to our little after-school review session here on units 4 and 5, energy and momentum. I think that these are probably, especially energy, like the most important of the sort of lenses that we have for the year. I do sort of like to think of each of the topics that we've got as a perspective, as a lens on how to view the world. And I really think conservation of energy is probably the most important. Conservation of momentum also a really, really big deal. Again, what are we going to work on? We're going to look to identify some key relationships and equations between forms of energy. We'll also talk, obviously, about momentum. And then figure out, again, our big job here, you know all the equations by now. Our big job is to figure out like what to do and when, right? When is this an energy question? When is this a momentum question? What are they actually asking us to do at any given time? So let's start with energy. The important thing, let's start with energy, of course. Energy we measure in joules. Joules is the same as newtons times meters, as becomes important in a moment. And the important thing is that energy is, the great thing about energy and momentum both is that they're conserved. Energy is always conserved in what's called a closed system. And if you remember, a closed system is one where nothing comes in, nothing comes out, right? Everything is contained within there. You do have to be a little careful about what's considered a closed system, right? If I like just drop an object, that object appears to gain a bunch of kinetic energy. It's only when you consider, they sometimes call it kind of the Earth ball system, that you realize, oh, well, where did that energy come from? It came from gravitational potential energy relative to the Earth. You do actually have to sort of consider, that's the Earth, as part of your system there. Most of these forces that we consider, springs, gravity, all these things, are what we call conservative forces, so they do conserve energy. You also get what are called non-conservative forces, things like friction. Friction's the big one. Strangely, some of them are also things that we think of as being pretty well-behaved forces. Tension is actually a non-conservative force because strings are really good at pulling, but not good at pushing. If I pull something one way, I can't just like push it the other. I gotta get my string over on the other side and get it going the other way. I don't just get the energy back for free the way that I do with gravity. If I pick something up and I drop it, I just get that energy back. In the absence of these other forces, in the absence of friction, air resistance, things like that, what we get is our total, they sometimes call this total mechanical energy. That is potential plus kinetic. Whenever they say total mechanical energy, they just mean potential plus kinetic, not including any other friction or anything. Otherwise, the total energy is just constant all the time. The system always has a total maximum amount of energy that it maintains. And so any potential energy you lose turns into kinetic, any kinetic energy you lose turns into potential. Sometimes we still like to look at energy through the lens of forces. And so it's really important to note that how do forces interact? Forces do work. And the way that they do work is, of course, force times distance, with that caveat that the force and the distance, the force and the displacement have to be parallel. They have to be in the same direction. Hopefully on your formula sheet, they do give you, right, if I've got a box and I'm applying some force at an angle here, and the box moves some distance d, it helpfully reminds me that it's FD cosine theta. Just like with torque, you want to be a little careful. You never want to take their word for it, that it's always the cosine of the angle that they give you. The point is that cosine here gives you the parallel component of force. So you want to make sure that they are in the same direction. What do forces do? They generate work, and work is exactly equal to change in energy. You can also think about the change in energy through the lens of power. Power, right? The one they give you on the formula sheet is that it's change in energy over change in time. It's worth remembering that this is also force times velocity. Again, with the caveat that the force and the velocity need to be parallel in this case for there to be power. Our unit of power is joules per second, also known as, I won't make the joke this one time, also known as watts. So that's literally how many joules of energy we use up every second. Energy is a little bit of a strange one. Most of the things we do in the year are vectors, velocity, forces, momentum, all these things are vectors. Energy is a scalar. It doesn't care about what direction you're pointing. And that actually makes it weirdly powerful because it lets us ignore a lot of inconvenient things. So, and as we'll talk about when we get to the little summary at the end, one of the things about energy that makes it really powerful is if I say have this roller coaster, I don't actually need to know the shape of the roller coaster. I don't need to know where I'm going, which way I'm going. All I really need to know is what's my initial height, what's my final height, what's my initial velocity, what's my final velocity, and I can do conservation of energy. I can put it all together. So for instance, if I have a roller coaster, as long as it goes a certain height delta, changes a certain height delta H, I don't really care what the shape of the hill is. It could even go down a little bit and then come back up. It could do a little loop and then come down. As long as that total difference in height is still the same delta H, the final velocity will be the same in the end. One quick thing you can do when you're doing this is the 0 for gravitational potential energy. You can put it wherever you like. Most often, you're going to want to put it at the low point. But sometimes it's convenient to put it somewhere else. You might want to put it on the ground. But you can always decide where 0 potential energy is. And that makes your life really easy because it gives you the opportunity to say, oh, well, I'm going to start at some place I have, say, pure potential, and I'm going to end someplace I have pure kinetic, and it makes my equations really, really convenient and really stand out. Otherwise, they're pretty nice. Most of these equations are on there. The potential energy of a spring, potential energy from gravity, all of this, kinetic energy, of course, all that is on there, which is nice for you. A few things that we need to be reminded of are work. How's it going, sir? Is work. So work is usually force times distance, but we always want to ask ourselves, what happens when the force is changing, right? When it's not a constant force? Well, in this case, we're looking for a graph of force versus distance, force versus displacement. If you've got a force versus displacement graph, the area under that graph is going to tell you the work. So knowing your graphs, if they give you the two axes, what does the slope mean? What does the area mean? In this case, the slope doesn't mean much of anything. The slope doesn't really mean much of anything for this particular type of graph. Okay. How do I know when it's an energy question? Well, the biggest way to tell that it's an energy question is that time doesn't really seem to matter. You don't really care how long something takes. You're really just comparing one point to another point. You're asking what's the energy here and what's the energy here and setting them equal to each other. And in this way, what it really does is it relates where you are, what your position is, and position here corresponds to kind of potential energy or maybe work done with how fast you're going with your velocity. So any of these questions where it's like, oh, you fall down a certain distance, how fast are you going? You can really look at these through the lens of energy. You don't care how long they take in this case. Often they involve springs or pendulums. They will involve, so there's a big connection between energy and simple harmonic motion. Force versus position graphs, as we just mentioned, you got to be able to find your work there. The big thing that I think of for energy is sort of the middle of our problem messy. So like if we look at some of these little examples here, I don't want to have to know the shape of the hill. I don't want to have to know exactly what angle it is or like, how the track is shaped. Conservation of energy doesn't care. All it says is no matter what the shape of the track is, I can compare this point to this point. We call this in math, we have a funny name for it that you might find later if you take multivariable. This means it's called independence of path. Independence of path. That's not going to really come up on the exam, but energy doesn't care how we get there. It just cares where we start and where we end. So again, conservation of energy is a really great tool for ignoring some of the messy details of exactly what a ramp or whatever looks like. I will say you got to be a little careful. The one case where energy is going to betray you a little bit is if you have a collision, two things sticking together, colliding. In that case, energy sometimes works, but you do need to, momentum is going to be your best tool for that. So speaking of momentum, let's talk about momentum. Momentum is also always conserved in a closed system. There's a reason that we put these two units together, because they're both conservation laws. Momentum is also always conserved in a closed system. Now, it is a vector, right? So in one dimension, you can have positive momentum and negative momentum. You can have like momentum to the left or to the right. In 2D, your total momentum is a vector that points off in some direction and is conserved in 2 dimensions as well. So if I have, say, an object moving this way and an object moving this way, they might end up moving this way afterwards, right? The y momenta are going to cancel each other out, but the x momenta are going to add up to make sure that we maintain the same total amount of momentum in 2 dimensions. They rarely ask 2D questions, but it is in theory something that could come up. So again, total momentum is conserved, right? If I've got the initial momentum of a system, it's the same as the final momentum, unless there's some kind of force. In these cases, forces provide impulse. So this is sort of the mirror image of work, right? Rather than force times distance is work. Here for momentum, we've got force times time, which goes by the name of impulse. The units for momentum, there's 2 units you could use, kilogram meters per second, kilograms, newtons times seconds also works, and they are exactly the same in this case. So impulse changes momentum, though they give you sort of the equation. Change in momentum is F delta T. You can expand that a little bit. This is our fat equals MAV equation. Change in, impulse equals change in momentum. And that's a really helpful one to have. The big thing about momentum is that you use it literally anytime 2 things stick together or collide or bounce off of each other. So if you suspect that things are colliding, 2 cars hit each other, we had that FRQ on our last exam where we had an object on a spring and we dropped another box on it and they stuck together. Well, that's a collision. It was maybe a subtle one, but it was a collision. Anytime 2 things stick together, conservation of momentum is going to be your best. And we'll review kind of the main types of collisions in a moment. Again, what happens if your force is not constant? Well, in that case, you need to look at a force versus time graph and find the area. And the area under that graph is going to be the impulse. Remember, right, we kind of did a little mini lab about this where we saw one of these graphs and found the area to get the impulse. We also saw an FRQ, right, where 2 things collided. Remember that, like, okay, what's the area under this graph? We're going to estimate that to be 90 and 20. So that'll be 1,800 Newton seconds or whatever of impulse. Remember, if one object in your system, if let's say there's a little force sensor and the 2 things bump and this is the graph you get, one object is going to gain that much, the other object is going to lose that much, right? It's always, momentum is always conserved. It gets traded in this case. So talking about those collisions, the 2 main types are elastic or inelastic. Elastic collisions are much rarer in our materials just because they're a little bit more complicated. In elastic collision, this is where it bounces, right? The 2 things bounce off of each other. In order for this to get a perfectly elastic collision, both kinetic energy and momentum are conserved. You don't lose a drop of energy. Kinetic energy and momentum are both conserved. These can get a little bit complicated to solve. You can do it. You can do some algebra and set up a system of equations. There is a special case that they want you to know about, which is if I have, 2 objects of the same mass, then when they collide with an elastic collision, they just trade velocities. So if one's moving at v1 and the other's moving at v2 after the collision, this one will be moving at v2 and this one's moving at v1. They just swap velocities. Most of the time we deal with inelastic collisions where momentum is still conserved. Momentum is always conserved, but you lose some kinetic energy. You lose it to heat, you lose it to friction. Inelastic collisions have a big, broad spectrum. Sometimes, quite often, in fact, you get objects that stick together, right? They stick together, in which case, before the collision, if you had M1 and M2, they sort of behave as like one big object afterwards. They move at the same velocity. That doesn't have to be the case. It is possible to have an inelastic collision where the things bounce off of each other, but still lose a bunch of kinetic energy. So that is possible to have happen. In real life, most collisions fall on some spectrum between perfectly inelastic and perfectly elastic. There's some bounce to it. But most of the time we get inelastic collisions. If they stick together, it's always, always, always inelastic. So just be on the lookout. Most of the time you can combine the masses together or split them apart. But sometimes, sometimes no. Sometimes they'll just be like, oh, this thing hit, this thing's going 4 meters per second and it hit something at rest. And then this bounces off and it's like 1 meter per second that way. How fast is the other one going? And it might still be inelastic. Some energy might still be lost, but you can do conservation of momentum to figure out how fast the other one's going. Just mind your pluses and minuses here. This comes up quite a lot where, right, this object goes from +4 to -1. That's a change in velocity of -5 because it went from 4 all the way down to -1. So do be cautious about those pluses and minuses. How do I know when it's momentum? The single best clue is things collide. It doesn't get much simpler than that. If things bounce off of each other, if things run into each other, it is always, 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 always momentum. So, you shoot an arrow into a pumpkin and it lodges in the pumpkin, or you smack two things together, or you slide one object into another and they roll off the table. These are all always, always, always momentum questions. Sometimes you'll get those impulse ones, time and velocity to mass or force. Quite often they will give you maybe on an FRQ like some force versus time graph, and they ask you to analyze it or find the area or something. So these are all good clues that it's momentum. So the last case that's a little bit weird is cases where your initial momentum might be 0. So let's say you've got a kid standing on a raft. I'm going to try to draw a kid standing on a raft. Initially, if everybody's at rest, the total momentum of the system is 0. If the kid starts to walk to the left, though, his feet are applying a force to the raft. He's going to walk to the left. The raft is going to slide to the right, and the difference in their speeds is going to depend on the difference in mass. Oh, there's one really important thing about momentum that I forgot to note, which is if I'm looking at the center of mass of a system, right? If I've got two objects that are colliding, and I kind of keep track of where the center of mass of the system would be. Here it would be closer to the bigger object. It turns out that the velocity of the center of mass of the system is constant if there's no external forces. So that comes up sometimes. It's a fairly minor aspect, at least in here. So let's go ahead and take a look at some examples. I'm going to run through some of the examples that I had, and then anybody in chat, or of course, Gabby, if you want to ask any questions that are more specific, we can pull them up, of course. So let's take a look at this first one. I pulled this one actually straight off of the end of our last exam. So here we've got a skateboarder riding along at 2.5 meters per second. So here they are, 2.5 meters per second. And again, I would always recommend you draw a picture when they encounter a hill. And at the top of the hill, they're going slower now. It's only 1.5 meters per second. And they want to know the height of the hill. And this is a perfect energy question because we don't care about the shape of the hill. We don't care about how long the hill was or anything. We literally just want to know how tall the hill was. And so here we can look at our energy. Now, we obviously don't know the mass of the skateboarder, so we're going to start by doing everything symbolic and hope that it works out. And if it doesn't work out, then we can always choose D. So we start out at the beginning here with some amount of kinetic energy, 1/2 mv initial squared. I can go ahead and just set my 0 of potential energy right here at the bottom of the hill. So I say I start with only kinetic, no potential. When I come here to the end, though, I still have some kinetic energy, 1/2 m v final squared, but I've also picked up some potential energy, right? Plus mgy or mgh. So I picked up a little bit of potential energy as well that I need to factor in. And what's nice here is by writing out the whole equation symbolically first of all, I can see if I'm missing anything or what I need to know, but I can also recognize that there's an m everywhere. And so I can divide away all the m's, which is nice because I don't know m in the first place. And so being able to get rid of it makes me feel a lot better. I can now multiply both sides by 2. Vi squared equals Vf squared plus 2gh. And I just want to pause for a moment and note that, as I've said sometimes before, this is basically the third kinematics equation. This is basically the third kinematics equation, which is why the third kinematics equation is secretly a work and energy equation rather than a kinematics equation. You can still use it like a kinematics equation. But, so our initial velocity squared equals our final velocity squared plus 2gh. So a little bit of solution, what does that get us? That gets us our height is going to be Vi squared minus Vf squared all over 2g. So if I go ahead to my calculator and I look at that, I get 2.5 squared minus 1.5 squared. So that top is 4 divided by 2 times g is 20, which should be 0.2, 1/5. So my hill is 20 centimeters tall. Yeah, sure. 20 centimeters is not nothing. 20 centimeters. All right. Cool. Let's take a look at the second one. And I wanted to pull this out because this is a power question. A constant force delivers a power of 4 watts to an object. If the object's average speed is 2 meters per second, then what is the magnitude of the force? This is an important place to remember that power is force times velocity. And in this case, we're delivering 4 watts of power. And we're going at least an average speed of 2 meters per second. Sometimes we're going slower than that, sometimes we're going faster than that, but that's okay. This is our average speed. And so in this case, our force here will be 2 newtons. 2 times 2 is, of course, equal to 4. Is there a different way to do this? There is a different way to do this, and I have to think about what that would be. This is actually probably the best way to do it. Is just power equals force times velocity. You could do this problem by making up a time. You could be like, this is a time of 1 second. So it's got 4 joules of energy, which is some force times, well, if we're going at an average speed of 2 meters per second, you can do this as work, right? 4 joules of work equals force times distance. We don't know our force, but over 1 second, if our average speed is 2 meters per second, we're going to go 2 meters. So again, we get force is 2. So you don't have to remember power is force times velocity, but it is a helpful piece at times. All right, I believe I'm skipping forward now to 4, 5, and 6 here. These are just, we've done these over and over and over again, and we will continue to do them over and over and over again, because especially number 5 is really important. Here, we've got a 4 kilogram box, and it's pulled 5 meters across the table. That's a big table, I'm just saying, by a string. And the tension in the string is 40 newtons, and it makes a 60-degree angle here in this case. And I want to find the work done by the pulling force. Well, in this case, let's remember that our work is going to be force times distance, but that the force and the displacement have to be parallel. So in this case, we're interested not in our full force of 40 newtons. We're interested in F cosine theta as our force. And last I checked, the cosine of 60 degrees was 1/2. So I believe this is going to be 20 newtons times 5 meters. So, which is 100 joules worth of work being done by our pulling force. Now, it does ask here what the normal force between the table and the box is. A lot of times these questions will involve friction. And the problem that we have is we've done so many problems where the normal force is equal to the force of gravity that we just get into this rut of being like, oh, it's equal to mg, it's equal to mg. It's not equal to mg. If we draw our free body diagram, we've got, of course, mg down. We've got normal force up. But we also have this other pulling force of 40 newtons. And that pulling force has two components here, one of which we've already found. It's also got a y component, right? We're pulling up on the box. And in this case, if our box is just sliding horizontally, then it's not Fn equals mg, it's actually Fn plus Fy, I guess I should be responsible, minus mg equals 0, right? The net forces in the y direction still add up to 0, but we can't just set Fn and mg to be equal. So here, our normal force is actually going to be mg minus the y component of our force. So we have to go figure out what the y component of our force is. That's going to be well, the x component was cosine. This is going to be f sine theta. So it'll be 40 minus 40 sine theta. And then I have to go to my calculator and make sure my calculator is in degrees. And if I work this out, I end up with like 5.36 newtons or so. So my normal force is actually pretty small. Why is my normal force so small? Well, this is not to scale. What's actually happening here is I'm pulling upwards with almost the entire weight of my box. Like my y component of this force is rather large. And as a result, the normal force doesn't have to work very hard, right? All we're demanding here is these two forces equal this force. So the normal force was gonna let up a little bit, it's gonna relax. This next one is if I had to guess, like if I had to bet money, which I'm not gonna do because there's 80 of you and I don't wanna take your money, or I was gonna say or lose $80, but like I just don't wanna take your money. If I had to guess one question that's gonna be somewhere on the exam, it's gonna be a question like this. What's the work done by the normal force? And the answer is not the normal force times 5 meters. The answer is nothing. Why is the answer nothing? Well, remember, our box is sliding to the right. The normal force is up. In order for our forces to do work, they have to be parallel. Well, how parallel is our normal force to our displacement? Well, it's not, right? They're at right angles. And in fact, if you want to be really scientific about it, this angle is 90 degrees. You look at our work formula, it's got a cosine theta, and cosine of 90 degrees is 0, is absolutely nothing. So the normal force does no work. Another way to think about that, right, is work changes energy. Does the normal force actually change the box's energy? No, the normal force just keeps the box from falling through the table. This force changes its energy. This force is going to speed it up. The normal force doesn't change its energy at all. It doesn't gain or lose gravitational potential energy. It doesn't go up or down. It just goes sideways. All right. What else did I have here? I also pulled out number 9 because it's always good to get these graph questions in here. So we have an object of mass 5 kilograms. Always good to note that. And experiences a force that varies over time as shown on the graph. So let's pause for a moment before we even read the rest of the question. We got a force versus time graph. Well, if we ever got a force graph, we probably want to be looking at the area under it. So in this case, let's go ahead and find that area. We'll split it into 3 chunks. The middle chunk is the easiest. It's 2 by 10, so this is 20. This is also 2 by 10, but it's a triangle, so this is going to be 10.
Kiraba Samunigus, if you are in the building,
this is going to be 1 by 10, but it's a triangle, so that'll be 5.
If you are in the building, please come to the main office. Thank you.
So the total area here is going to be 35, excuse me, newtons times seconds. This is an impulse question. Force times time gives us impulse. So this force, whatever it is applying an impulse of 35 newton seconds. It then says the object started at rest, so it had an initial velocity of 0. Then what's its final velocity at the end of all of this? And here's where we can just go fat equals math, right? Or impulse equals m delta v. F delta t only really works if we have a constant force, but fortunately, we know what our impulse is. We know it's 35. So 35 is our impulse, and our mass is 5. So 35 equals 5 times v. And in this case, and I can just write v because remember this is v final minus v initial, and our v initial here is nothing. So how much does our thing change by? Well, 35 over 5 changes by 7 meters per second in this case. So just pay attention to those graphs. They give you a graph, you're gonna have to use it in some way. All right, 13 and 14, and then I think I picked 2 more out, and then we can take a moment and do any last ones that people want to do. Here we've got a bullet that impacts a stationary wood block, and it embeds itself in the block, and then they both slide. Well, what kind of question do we think this is? Momentum, absolutely. The two things collide. This is a momentum question. So let's go ahead and draw our picture here. We've got our bullet, little m v, and it embeds in a big block. That's big M. And then afterwards, they're going to slide together. And it's important to note there's a difference, right? You might have cases where the bullet bounces off. You might have cases where the bullet embeds itself. You might have cases where the bullet goes right through. Here, the bullet's going to embed itself. Fun fact, if the bullet bounces off, it actually imparts more impulse to the box, because if you think about it, the delta V of the bullet is larger if it bounces off. Here, the bullet sort of mostly comes to a rest. You actually get more momentum transfer if it bounces. In any case, let's look at this through conservation of momentum. At first, the block is at rest. So all of the momentum is in the bullet. So if we look at the initial momentum of the system, it's a mass of 0.02 at times a velocity of 700 meters per second. So I can go ahead and calculate that. Yeah, I did this right. 0.02 times 700. So it's got a momentum of 14 Newton seconds, or 14 kigums. The units are the same to begin with. Well, after the collision, how much momentum does the system have? No, the exact same amount, 14 kigums. So that 14 kigums needs to be equal to, well, now the total mass of our system is 4.02 kilograms, because, well, it's the mass of the block plus the mass of the bullet. They're moving together now, times whatever our final velocity is. Let me write that a little bit more clearly so you can read that this is 4.02 kilograms times our final velocity. So if we take that and divide it by 4.02, we end up with about 3.48 meters per second in this case. It's considerably slower. I mean, it's still like 6 miles an hour, but it's a far cry from the 700 meters per second that we started with. Now, here, it asks us for the ratio of kinetic final to kinetic initial. Let's take it extremely literally and calculate each one. M v squared 1/2 little m plus big M v final squared, right? Let's go ahead and calculate our initial and our final energies. Now, I'm going to leave the 1/2 off because they're going to cancel anyway. So if I just do little m v squared 0.02 times 700 squared, I end up with 9,800 on the top times 3.48 squared. And let's round off 48.7 on the bottom. Oh wait, no, I did this wrong. Woo! See, I'm going to get the wrong answer. I did this wrong. What did I do wrong? What did I do wrong? It's supposed to be final over initial, right? Is this the final? Oh. No, I swapped it. So, oops, these are supposed to be switched. See? Human beings. So let's just do that now. We'll switch it over. 48.7 divided by 9,800. Fortunately, I did my division and I got a number that wasn't on that list, which is a good sign. And when I do it this way, I get 0.00497. So I'm going to go with A in that case. What that means is if I multiply by 100, we have basically 0.5% of our energy left. So in this collision, we lost 99.5% of our kinetic energy, which, I mean, not to get too morbid about it or anything, is actually sort of the point of a bullet, that you give it a bunch of kinetic energy, and when it impacts, it gives up all of that kinetic energy. So all that loss of kinetic energy is going to go into damage to the wood block, into heat, into like breaking the wood. Your object with a bullet usually is not to knock something over, it's to put energy into it. And in this case, we've put quite a lot of energy into it. Okay, these were the last two that I had pulled up, but obviously we can go over a couple more as well. I wanted to look at a force versus displacement graph, and again, force versus displacement should immediately make you think work in this case. So this is the counterpart of the impulse question before. So here is force versus displacement. Now, this is a little interesting because we have both some positive forces and some negative forces. So let's find the area carefully. So we'll break this up into, I'm actually going to do a funky thing. I'm going to break it up into some regions here. I'm going to break it up like this. And I know that this seems a little strange, but I promise it will make sense. You don't have to do it like this, certainly, but I think this will make some sense when you do it. If we look at this, we've got, this is 2 by 3. There's 6 joules of work. You know what? Now we have to deal with the trapezoid. So I'm reversing my earlier position. Now we have to deal with the trapezoid. Nobody likes trapezoids. We got 6. Here we've got 1, 2, 3 by 1, 2, 3. So the area, this will be, well, 9 divided by 2. So this will be 4.5 joules. What do we think is going to happen now? So all of this energy, all of this work is going to go to increasing its energy, right? Well, what about when we start pushing the other way? Yeah, we're going to decrease the energy. So this one has an area of minus 0.5 joules. And then this one has an area of minus 1 joule. So if we add up the positives, we get 10.5. Minus a half gives us 10, minus 1 gives us 9. So the work done by this force is a total of 9 joules of force. Or not 9 joules of force, 9 joules of energy, 9 joules of work. So we do 9 joules of work on this object. The nice thing is, what tends to trip people up sometimes is they do this and they're like, okay, then, well, where does that energy go? You know, we did 9 joules of work. Where is it now? Yeah, it's in kinetic energy, exactly. The object has increased its kinetic energy by 9 joules. Now, conveniently, it started at rest. So it started out with 0 kinetic energy. Now it just has 9 joules of kinetic energy. So we can go ahead and solve that out. 1/2 times 2 times v squared. Isn't that nice? 1/2 times 2 cancels out. V squared equals 9, gives us, 3 meters per second in this case. So that one was pretty good. Again, it's the same, find the area under a graph. It's just instead of being momentum, this time it's energy. This is the last one in this section, but of course we can go back and do a couple others. We've got a cart of mass 2 kilo. Okay, I need to change that in the future. It says 2. Make a note to turn that into a kilograms. Proofreading there. It's moving at 6 meters per second. And again, I'm just always be drawing pictures. So I know that you're pressed for time, but on the exam, just quickly sketch a picture of your system. So it's moving along a horizontal surface when it encounters a rough patch. So here's our cart. I promise it'll actually make you faster. 6 meters per second. When it encounters a rough surface, it manages to make it 9 meters into the rough patch before it stops. And it wants us to find the coefficient of friction. All right. Well, this is an energy question because we've got some friction and it's dissipating all of our energy, right? It's dissipating all of our energy. You could, in theory, do this as like a forces question. You could do this as a forces question. We're not going to. In fact, I didn't even need to provide you with the mass. I was nice and I did so. But I didn't even need to provide you with the mass in this case, I think. Because we start out with some energy, right? We start out with 1/2 mv squared worth of energy. We end with nothing, right? We end with no kinetic energy. We haven't gained or lost any potential energy. So the question is, where did all that energy go? Yeah, into friction, into work done by friction. So the work done by friction here, right, is going to be the force of friction, force of kinetic friction times distance. The force of kinetic friction, well, there's nothing funky going on in the vertical direction. So this is going to be mu times the normal force. And the normal force will just be mg. There's no, here we can safely assume that. So we're going to end up with mu mg times d. So here's our kinetic friction force times d. And now we can do a little bit of solution. We can get rid of our m's. And what we find here is, let's see, mu is going to be v squared over, I'm going to divide by these things, 2 GD. V squared over 2 GD. Of course, you're given the mass, you could always calculate everything out perfectly. 6 squared divided by 20 times 9. And in this case, I get a mu of. And one way to think about this equation, right, is if I increase my distance, right, that is, if it makes it further into the patch, well, if it makes it further into the patch, my mu must be lower, right, dividing by a bigger number in this case. So, all right. Were there any others from this section that you wanted to talk about? Yes, we can go over 11 and 12. Let me pull those up real quick. Yeah, okay. So a sort of energy, sort of projectile motion question for 11 here. It says if you throw a ball at an angle instead of straight up, which of the following is true at the apex of the ball's trajectory? So let's just remind ourselves before we even start reading the options, right? What is the thing that's true at the top of the ball's trajectory? Which velocity is 0?
Y.
Yeah, the y velocity is 0. We still have some x velocity, right? So as a result, will the kinetic energy of the ball be 0? No, there's still some energy in the x direction. Well, I mean, energy is not a vector. Energy is not in the x direction, but we still have some x velocity. We don't ever quite lose that x velocity. We can't. We never get to a point where the kinetic energy is totally perfectly 0. As a result, will the total energy of the ball be mgh? Well, down here, if we start off with some initial velocity v0, we'll have 1/2 mv0 squared, right? Are we going to be able to turn all of the energy into potential energy? No, because there's still some kinetic energy left, right? It's going to be mgh plus a little bit of kinetic energy, because again, we're still moving in the x direction. And this is a similar way of asking, did we actually convert all of the ball's initial kinetic energy to potential? No, most of it, but not all of it. So the answer is actually none of these. That there is still a little bit of kinetic energy left at the top that we can't get rid of. We can't get rid of in this case. Can't get rid of. All right, and for number 12, for an inelastic collision, let's remember, first of all, that linear momentum is always conserved. Linear being not angular momentum, not rotational, which is also conserved. Linear momentum is conserved. So anything that doesn't involve 1 is straight out. And then the last two, do we conserve energy in inelastic collisions? The answer is, well, I mean, we can actually go look at that. Where is it? Where is it? Here, look. We had an inelastic collision. Did we conserve energy? Nope, we lost most of it. Inelastic collisions don't conserve energy. They don't conserve kinetic. They don't conserve potential. I mean, the energy still exists. It just is lost to friction or heat or sound or whatever. So in this case, for an inelastic collision, the only thing you can count on is that momentum is conserved. Everything else is out the window. If there were elastic collisions, then it would be okay. I don't know if they would write it exactly this way for an elastic collision, but definitely if it were elastic, then kinetic energy would be total kinetic energy. So, any others that you wanted to take a look at today?
Could we do 7 and 8?
Let's take a look at 7 and 8 real quick. Seven is a good philosophical question. So let's start with 8. Let's go backwards here. Oops. All right. Let's start with 8. A 1,000 kilogram car moving initially at 20 meters per second brakes on a horizontal road with an acceleration given there. What is the average power required to bring the car to a stop? Now, there's a couple ways to do this. The first way to do this is the most straightforward. And so we're going to do the straightforward one first. The straightforward one is to remind ourselves that power is change in energy over change in time, right? In this case, for the energy, the car starts off with a lot of kinetic energy, right? And it ends with how much energy? 0. It ends with nothing, right? So how much energy does it lose? It loses all of it. It loses all of the 1/2 mv squared that it started with, right? And in this case, we know the initial velocity. We can actually calculate exactly how much energy it loses. 0.5 times 1,000 kilograms times 20 meters per second squared. It loses 200,000 joules of energy. Quite a lot of energy. All right, well, if we're gonna do this, now what we need to do is we need to figure out how much time does that take, right? So let's pause for a moment and remember there is one part of physics, that one of our units that is obsessed with time. How do things change over time, right? What's our most time-based thing? Let's see what we got. We've got an initial velocity. We've got a final velocity, right? It ends at rest. We know an acceleration, which is presumably going to be negative, right? We're looking for a time. What is this feeling like? Kinematics. Oh yeah. We've got 2 velocities and acceleration we want a time. Let's go ahead and look at our first kinematics equation, which tells us, of course, that how velocity changes over time. V final is V initial plus acceleration times time. Well, our final velocity is nothing. 20 minus 3t, right? So we can solve for t there. And we get a somewhat odd number, 20 divided by 3. We get like 6 2/3 seconds. It takes about 6 seconds to stop, right? You start at 20, every second you lose 3. Well, it takes you 6 and change. So now we can do 200, 1, 2, 3, divided by that time, 6.67 seconds. It turns out to work out very nicely. This gives us 30,000 watts of energy. 30,000 watts of energy, which is 10,000 is 10 to the 4th, so the one that starts with the 3. There is another way to do this, which is to look at to try the force times velocity thing. And you might say, oh, well, I know the force because F equals ma, right? So 1,000 times 3, I've got a force of 3,000 newtons. Here's the rub. If we're looking for average power, one of these things needs to be average, right? Our force is constant, but our velocity is changing. If I start out at 20 meters per second and I go down to 0, what's my average velocity? 10, right? I spend half the time above 10 meters per second, half the time below 10 meters per second. So in this case, 3,000 times 10 gives us the same answer. So that one is a little tricky. I think the energy divided by time is the more reliable way. 7 is a strange philosophical question. So let's consider 2 objects. right? M1 and 2. They have the same momentum. So that means M1 times V1 equals M2 times V2, right? So let's make some things up. Let's make some things up. And one thing you can always do if things are getting too abstract is make something up. So let's take a, I don't know, give me a mass one. 5 kilograms. It's 5 kilograms and it's moving at 2 meters per second, right? So 5 times 2 is 10. Here's M2. M2, just because of the way the question is phrased, M2 is going to be a 10 kilogram mass. In order to have the same momentum, it needs to be moving at 1. Yeah, moving slower. All right, they have the same momentum. 5 times 2, 10 times 1, same number. Let's calculate their kinetic energies. For 1, we've got 1/2 times 5 times 2 squared. 2 squared is 4, divided by 2 is 2. This is going to have 10 joules of kinetic energy. The other one, 1/2 times 10 kilograms times 1 squared, is only going to have 5 joules of kinetic energy, right? So these two objects have the same momentum, but object 1 has more kinetic energy. And why does object 1 have more kinetic energy? What? It's moving faster. Notice there is a second option that we could use, which is we could say if object 1 has less mass, because if their momentums are the same, has less mass and is going faster, are sort of the same. Notice that this option is scrupulously missing so as not to confuse you in this case. So this one is we're looking for if it's moving faster. And the way to think about that is not just our calculation, but momentum doesn't care which is which. Momentum thinks that mass and velocity are the same. You're just multiplying together. Kinetic energy cares way more about velocity. So a small object moving quickly and a big object moving slowly might have the same momentum. A small object moving quickly will typically have more kinetic energy. And this has some weird effects at the high range of velocities. The one that comes to mind off the top of my head is space junk, space debris. You have a real That's weird. Everything just started shaking. Earthquakes are not unknown around here. In any case, space junk. If you've got like a little fleck of paint that came off the space shuttle, it came off some rocket, or a little screw or bolt or like a chip of metal. The problem with those in space is even though they're really, 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 really tiny, like a fleck of paint isn't going to hurt you on Earth. In space, right, they're going like 8,000 meters per second. Because you have to be going that fast to stay in space. Actually, maybe a little bit slower than that, but still quite fast. Let's go. Fine. We'll downgrade it to 7,000 meters per second. And the other problem is, right, you don't know which way they're moving. It might be going 7,000 meters per second this way, and you might be going 7,000 meters per second the other way. And now it's coming at you at 14,000 meters per second. And that v squared comes into play. And so you can get these tiny little chunks of paint or an errant screw and have it like punch a hole in your spaceship. And there's sort of scary pictures from the International Space Station of like a big, thick plastic window that's got a giant, it's not broken, but it's got a giant divot in it from a little grain of dust or something that hit it going, 10,000 miles an hour. So stuff goes really fast. All right, I've got to log off. I'm going to post this video up. Thank you so much for coming, and I will see you in class.